Welcome back everyone. Today we are going to discuss this important topic of physiology, that is cellular fluids. It's a very important topic, very short topic also, nothing much discuss, but very important in physiology. Let's go. So let's start with this compound water. Water, which is the major contributor of body weight. Our body weight's major contributor is water. So standard terms, in an adult male of 70 kg, okay, an adult male of 70 kg, nearly 60% of body weight is water, which is nearly 60% 70 kg is 42 liters. First important point to remember. Then 18% of weight is proteins. 18% of weight is proteins. Then 15% of weight is lipids, and 7% of weight is minerals. These are some of the facts about body weight and water, protein, lipid and minerals percentage. These three not so important, but this is very important. 60% of body water in what? In 70 kg average adult male, that is 42 liters. This is first important fact to be remembered. Okay, so let's expand our discussion on water. It's water or in our body is determined by, remember, this TBW is equal to total body water. Okay, so this is a cell of our body. Okay, this is ICF, intracellular fluid. Outside of the cell, this is ECF, very simple, extracellular fluid. Extracellular fluid. Okay, ICF and ACF. This total body water, which is equal to intracellular fluid plus extracellular fluid. Total body water is equal to intracellular fluid plus extracellular fluid. Next important point to be noted and remember. Next, out of this total body water, ICF, okay, this is 2/3. This ECF is 1/3. ICF is 2/3, ECF is 1/3. Remember, total body water in a 70 kg man, which is 60%, is 42 liters. We have established here. Okay, this 42 liters, 2/3, which is how much? 28 liters. Remaining 1/3 of 42 liters is 14 liters. So ICF total is 28 liters, ECF is 14 liters. ECF 1/3, ICF is 2/3. Total body water is ECF and ICF. ECF is 14 liters, ICF is 28 liters. Remember, ICF is 2/3, ECF is 1/3. This next another point to be remembered. Okay, these are all only facts, nothing much to understand here. So we're going to discuss one by one. First is our extracellular fluid. Okay, this extracellular fluid, we have first extracellular fluid is our fluid between two cells. Okay, this is cell 1, this is cell 2. In between these two cells there is this fluid. Okay, what is this called? Interstitial fluid system. Interstitial fluid system. The second extracellular fluid, you want to see, this is the blood vessel, and this is our dear RBC. Okay, here, what is this? This is the plasma. Okay, this is plasma in which RBC and other cellular components of the blood are present. This is the plasma. ECF, what is ECF? This is combination of interstitial fluid and plasma. Simple, very clear understanding, self-explanatory. Interstitial fluid system as well as plasma, they combine to form the extracellular fluid. Okay, another subtype we have here is called transcellular fluid. Okay, this transcellular fluid is a special type of ECF. It's a special type of ECF. Transcellular fluid is total of 1 to 2 liters. 1 to 2 liters. Example of this transcellular fluid are pleural fluid, okay, pericardial fluid, then are this synovial fluid in the joints, and intraocular fluid in the eyes. The aqueous and vitreous humors, this intraocular fluid. Pleural fluid in the lungs, pleural fluid in the pleural membrane, between two pleural membranes. Pericardial fluid, pericardium in the heart, between two pericardial membranes. Synovial fluid in the joints, intraocular fluid in the eyes. Very frequently asked question on this transcellular fluid. It's a special type of ECF. Remember, it is not included in ECF. ECF is only our interstitial fluid combined with plasma. Okay, this transcellular fluid is a special type of ECF. It's total of 1 to 2 liters. Pericardial, pleural, synovial, and intraocular fluids. It's a special type of ECF. Remember, it is not included in ECF. Okay. Then we have to see in females, total body water is 50% of body weight. Okay, in males, we have discussed in average male it is 60%. Okay, in next is in children, the total body water is equal to 70% of body weight. Okay, so in children it is more. So total body water, if we want to see, it is maximum in children, then in males, then in females. The lowest is in females. 70%, remember, is children, 60% in males, females it is 50%, it is the lowest. So why this disparity between males and females? Why male is greater than females? Is due to more fat content in females. Okay, so estrogen hormone in females, it is lipogenic. It is responsible for production of more fat. Due to more fat content in females, remember, due to estrogen hormone. Okay, remember, body water, okay, inversely proportional to body fat. We have established above. Why total body water in males is greater than females? Due to more fat content in males, and body water is inversely proportional to fat. Okay, next topic we are going to see is lean body mass. Okay, lean body mass. This lean body mass is required to remove the effects of fat. Okay, this lean body mass is equal to body mass minus adipose tissue fat plus non-adipose fat, okay, combined with bone mass. Okay, it is the body mass subtracted adipose tissue fat, non-adipose tissue fat, and now we also include this bone mass. This formula will lead to our lean body mass, LBM. We used to remove the effects of fat, calculation of body water. Okay, remember, water content of lean body mass, okay, is equal to 70 milliliter per 100 gram of weight. Very important number, need to remember. 70 milliliter per 100 gram of weight is water content of lean body mass. Okay, lean body mass is body mass excluded from adipose tissue fat, non-adipose tissue fat, and bone mass. Okay, it is 70 milliliter per 100 grams of weight. Next is we are going to see is this measurement of body water. Okay, measurement of body water. Okay, yes. So this is the Stewart Hamilton method. Stewart Hamilton method. Okay, what we do in this, that the concept is that suppose this is a container, this contains some volume of fluid. Okay, containers containing some volume. We need to calculate this volume. Okay, how we need to calculate? We are going to inject. Okay, going to inject an indicator. It's an indicator, it's chemical compound we inject to the volume. So we have a formula, basic formula, it is amount of indicator is equal to concentration into volume. Okay, it is A is equal to C into B. Very simple. We need to calculate this volume. We need the volume. We are measuring body water volume. Okay, this V is A by C. We know the amount we have injected. We know the concentration of the indicator. We both know this. By dividing the amount in this concentration, we will get this volume of the fluid we have. This is called, remember, indicator dilution method. Indicator dilution method. Remember, for human body, okay, volume that we measure is equal to amount injected minus amount excreted divided by the concentration. Okay, this is the formula for human body. Human body, we when we use an indicator, some amount we inject, some amount gets excreted. Not all gets excreted, some gets absorbed also. So amount injected minus amount excreted divided by concentration, which gives the volume of the fluid we are going to measure. Okay, this is for human body. This is some indicators. Okay, This is the fluid. You want to see, this is the indicator. Very important table, see carefully. For total body water, okay, we are determining water, so we will use deuterium oxide and tritium oxide. Deuterium and tritium oxide, these are the radioisotopes of water. Deuterium and tritium are the radioisotopes of hydrogen which are combined with oxygen to form deuterium oxide and tritium oxide. So remember, total body water is deuterium and tritium oxide. Okay, next we are going to determine extracellular fluid. Okay, for extracellular fluid we are going to use most commonly, okay, inulin most commonly used. Also we are going to use mannitol, sucrose, sodium thiosulfate. Most commonly for ECF we use insulin. Also use mannitol, sucrose and sodium thiosulfate. Then we have for plasma. For plasma, in bracket, remember, we have plasma proteins, so we use radioactive albumin. Very easy to understand, radioactive albumin. And also remember, Evans blue dye. These dyes are very commonly used indicators. Okay, so also this indicator dilution method is also known as, remember, dye dilution method. This is the original Stewart-Hamilton method. The indicators we use most commonly are the dyes. Okay, also called dye dilution method or indicator dilution method. So in plasma we have proteins such as albumin, so use radioactive albumin. And one important, Evans blue dye. For ECF we use sodium thiosulfate, mannitol, sucrose, most commonly in inulin. Remember, inulin, not insulin, inulin. We use this inulin also in glomerular filtration test determination. We will see that in renal physiology. And for total body water, remember, water contains what? Hydrogen, which is H2O. The radioactive forms of hydrogen, deuterium, tritium. So deuterium oxide and tritium oxide. Very simple. So these are some of the indicators we use for total body water, ECF and plasma. Okay. Now suppose this is a blood vessel. Okay, this is a blood vessel. You need to see, we use the above seen indicators and dyes. Okay, we introduce a dye in our body into the blood vessel. Okay, this dye completely diffuses out. So the volume we calculate is equal to amount divided by concentration. This is the accurate formula. Okay, if this dye completely diffuses out, okay, the concentration of dye in the plasma falls. Okay, this dye needs to stay here in the blood vessel to get this proper formula in the volume. If this dye completely diffuses out, the concentration of the dye in the plasma falls. Okay, nothing too much to understand here. The concentration of the dye in the plasma falls if it completely diffuses out. Okay, as the concentration falls, volume increases. This in this formula, V is equal to A by C. Concentration falls, volume increases. Okay, inversely proportional, volume increases. This will lead to falsely high value. The volume we will get if the concentration falls is false. First it is false, okay, it's not true, and it is high. As the concentration falls, it is falsely high. Okay, so that's why we use Evans blue dye. It does not cross the plasma membrane. This Evans blue dye we use for plasma. Over here for plasma we use this Evans blue dye. It does not cross the plasma membrane, so it does not diffuses out, and it does not give falsely high volume numbers. So with this Evans blue dye. Okay, next for blood volume, okay, we use, remember, chromium tagged RBCs. Chromium tagged with RBCs. Okay, for blood volume we use chromium tagged RBC. Now this formula, blood volume is equal to plasma volume, blood volume is equal to plasma volume minus divided by 1 minus hematocrit. Important formula. This blood volume, this determined by chromium tagged RBCs, and the formula is plasma volume divided by 1 minus hematocrit. All the values will be given in the question. Okay, it can also give plasma volume, and hematocrit volume will also given. Will be asked to determine blood volume, or even blood volume can be given. Hematocrit value will be given. Will be asked to get plasma volume. So blood volume is equal to plasma volume divided by 1 minus hematocrit. Okay. Remember, in children, the blood volume is equal to 70 milliliters per kg of body weight. Children, this blood volume is 70 milliliters of kg per body weight. Okay. Now you've seen some methods of determination of blood volumes, use of dyes, use of indicators. So there are measurement of body fluids. Okay, there are some types here. Okay, some types here we are going to see. First is the direct measurement. Okay, this direct measurement of body fluids. For this we have indicators available. Okay, what we have seen before, first is the total body water. So next we saw the ECF, third we saw the plasma, fourth we have seen blood volume. TBW, deuterium oxide and tritium oxide, ECF, inulin, mannitol, sucrose, and also sodium thiosulfate. Plasma we used radioactive albumin, also Evans blue dye. Blood volume, chromium tagged RBCs. These are direct measurements. Why? Because these are indicators are available. We can calculate the volume by this formula. We inject into the body and measure. Then there is indirect measurement. Okay, indirect measurement. For what? For no indicators available. As no indicators available, you need to measure them indirectly. These are, remember, intracellular fluid and interstitial fluids. Two eyes, I for I, indirect, intracellular, interstitial, no indicators available. Okay, direct and indirect. So how we will get intracellular fluid or ICF? We know total body water is equal to ICF plus ECF. We will get total body water and ECF from direct measurement, and ICF simply subtract ECF from total body water. We get ICF. Next is interstitial fluid. We know this extracellular fluid is equal to interstitial fluid plus our plasma volume. So we get this extracellular fluid from direct and plasma volume from direct measurements. Okay, so interstitial fluid we merely subtract from plasma volume from ECF. Okay, this is how we get intracellular fluid and interstitial fluid. Okay, interstitial and intercellular fluid are indirect measurements as there are no indicators available. We get through these formulas. Remember, directs are ECF, total body water, plasma and blood volume. Next, I'm going to see some ions and molecules which are present in both ECF and ICF. Water and ions here. Okay, in ECF we have the cations. Cations in ECF are sodium, which is dominant. Here cations are potassium, magnesium, where in ICF these are dominant. Next is anions. Anions we have chloride. Here anions we have phosphate and also proteins. Proteins are negatively charged in ICF. These are dominant. Okay, I have also said this in the membrane potential discussion. In ECF it is outside. The dominant are sodium, chloride and calcium in majorly, and in inside there is potassium, phosphate and proteins. Okay, in the ECF pH is 7.4, slightly basic. Here the pH is 7.0. Intercellular pH is nearly neutral. Some of the facts we need to remember in ECF and ICF. Okay, so next we are going to see this body water loss. Okay, body water loss. Remember, through sweating we lost 100 milliliter per day. Okay, then there is insensible water loss. Okay, insensible water loss, that is evaporation from skin and lungs. The sweating is sensible. We know that we are sweating. This is 100 milliliters per day. But this insensible water loss, we don't know anything about this. We don't sense this. That is evaporation from skin and lungs. This is a very high value. Remember, 600 to 700 milliliters per day. So in all total, nearly 800 milliliters or nearly 1 liters of water we lose every day through sweating, 100 milliliters, and insensible 600 to 700 milliliters. Okay, next we are going to see that the cell shape changes. The cell shape changes. Okay, first case, now to see this cell. This cell is subjected to 0.9 NaCl, which is 150 milliosmol per liter of NaCl. Okay, 0.9 NaCl or 150 milliosmol per liter of NaCl. This is considered, remember, isotonic solution. We know isotonic solution, there is no change in cell shapes, no change in cell shapes. Okay, next scenario we are going to see the cell is subjected to 300 millimoles, not osmol, millimole per liter of urea. This is considered hypotonic solution. This is a 300 millimoles liter per urea. This is considered hypotonic, and when hypotonic solution is administered, it takes water inside, the causes lysis of cell and burst. There is cell swelling, lysis of cell, and bursting of the cell as it takes water inside due to a hypotonic solution. So in hypotonic solution, cells swell up and burst. Okay, just example 300 millimole liter of urea. Third scenario, cell is subjected to 300 millimole per liter of mannitol. Okay, this is considered to be a hypertonic solution. So this cell has water washout. Here water goes inside, water washout. There is simple cell shrinkage. Here cell swelling and bursting, here cell shrinkage in hypertonic solution, cell bursting in hypotonic solution. Remember, hypertonic is 300 millimoles of mannitol, hypotonic is urea, and 0.9 NaCl is isotonic solution. We give this in salines. In saline hospitals we give this 0.9 NaCl, which is 150 milliosmol liter of NaCl. Okay. Next we are going to see this plasma osmolarity. Okay. Remember, the plasma osmolarity value is 300 milliosmoles per liter. Okay. Its contribution, major contribution is 270 milliosmoles per liter. This is from sodium ions, very important. Remember, major contribution 270 milliosmoles per liter is from sodium ions. Minor is from proteins such as albumin, which is 0.75 milliosmoles per liter. The reason here being, why proteins such as albumin attribute such low value is high molecular weight and low concentration. Their molecular weight is very high, the proteins, the plasma proteins, but their concentration is very low, so they aren't able to influence the plasma osmolarity. So very low contribution, 0.75 milliosmoles per liter. Low concentration and high molecular weights. So this was all about plasma osmolarity. Last thing we are going to see is this Darrow-Yanet diagram. Okay, this Darrow-Yanet diagram, simple diagram, nothing much. We have this box representation. It's not a box representation, it is actually an x-axis and y-axis. On x we have volume in liters, and y-axis we have osmolarity. Okay, volume in liters and osmolarity, that is concentration. And this box is divided into two parts, not two equal parts. This bigger box, this is, remember, ICF component, 2/3 of total body water. We have seen this from starting. The osmolarity is 300 milliosmoles per liter. Okay, this component is obviously ECF component. This is 1/3 of total body water. Okay, this is the derived diagram. This diagram actually alters in various cases, such as diarrhea, syndrome of inappropriate aldosterone secretion, also when saline is introduced in the body, in hypertension also. Okay, so this is all about the body fluids. Very important discussion, short discussion, nothing much. The values you need to remember and important. A lot of questions and MCQ asked in exams, both in university and entrance. Please to revise them. I will catch you in the next one, guys. Thanks for watching and good luck.